Can you guys see the screen?
Yes, sir. Yes, sir. I can see.
Okay. Okay, when we use our conventional circuit theory, okay, well, conventional circuit theory means like the kind of circuit theory that you used in your electrical circuits class, right? In that case, you assume your wavelength is much, much bigger than the length of the circuit. Do you guys get me? What's the picture here? The wavelength is much bigger than the length of the circuit. So in that case, you can use conventional circuit theory to analyze. Okay. When we come to microwave engineering, the circuit length is comparable to the wavelength. So therefore, the conventional circuit theory doesn't apply anymore. So in this case, we have to consider the transmission line effects in order to design our microstrip circuit. So we will talk about the various transmission line effect. You guys follow so far?
Yes, sir. So far, so good, sir.
Yes, sir.
Okay, ideally, let's say you have a piece of resistor, call this R. Ideally, if I plot this resistor, says the resistor value is 500 ohms. So if I plot the resistor value for a range of frequencies, okay, then because you know, resistor is not a function of frequency, so you're going to get a straight line, right, at 500. Ideally, a resistor. Hello? Can you guys follow this?
Yes, sir.
Yes, sir.
Okay. But what happens, this is at AC. Ideally, this is at low frequency. Call this AC. Okay, those guys, I don't have any question. Please mute the mic, please. At high frequencies, the resistor is a resistor R. You know, all resistors, no matter any resistor is also a wire. Okay, the resistor has some kind of lead. So the resistor will have lead inductance, L over 2. On both sides, L over 2. And the resistor also have a capacitor this is a complete model of resistor, a capacitor called CA, charge separation. Please mute the mic, please. So this inductance, it's outside here. Okay, guys, let me repeat. If you listen to these things carefully, it's going to be very easy. If you're not listening, from the input to the output, and this is called, let's call this a C subscript B, and it's interlead lead capacitance. Interlead capacitance. Actually, this is the complete model of a capacitor. So I can simplify this model further. If I combine these two, I can combine these inductors here. Since it was L over 2 here, it was L over 2. So I can combine L over 2 inductance can be added, right? Inductance can be added. So if I add this inductance, the simplified model, those guys are sitting back there checking their WhatsApp, doing all kinds of nonsense. You're going to pay the price. So I can combine those capacitors and put them as a single L over 2 plus L over 2. You can say call this L. The R remains there. And CA is usually very small. CA is usually very small. This capacitance CA is very small, so we approximately set it to 0. So capacitance is 0. Okay, that means it's open circuit. Sorry, not CB. CB is approximately 0. CB I'm talking about is this CB here, right here. It approximately, usually is too small and we can just ignore it. So the net CA is going to be, so this is the simplified model. So I just can simply call CA to be C. Okay, this is a simplified model. So any questions so far?
Sir, so the L is actually equals to L over 2 and L over 2, is it?
Beg your pardon?
The L, right? Is it including of the both of the L over 2, sir?
Say that again, which L over 2?
there's a LO2 on the top, right, sir? And then in the simplified model, there's only one L, right? So does the L stands for both of the LO2, sir?
Yeah, because there's a L over 2 here.
Okay.
Okay, if there's a L over 2, and there's also another L over 2 here,
Right.
I can combine this into L.
Okay, sir. Thanks, sir.
Right, okay.
So then how CB becomes like very near to 0, sir?
CB,
Why? Yes.
yeah, because a CB, if you really do a simulation, then you will see that CB literally has no effect. For example, let's say CB is 1 femtofarad. Let's say 1 femtofarad is how big? How's
15, sir. Negative 15, sir.
Okay, thank you. Negative 15. Okay. Negative 15. That's a very good question. So CB.
Thank you, sir.
CB, right? Okay. So now I want to find the impedance caused by this capacitor. 1 over j omega C B. Let's say, just assume omega is 1 giga. Okay. Let's assume that omega is 1 gigahertz.
Okay, sir.
Just assume that frequency is 1 gigahertz, and then omega is around 2 pi f, right? 2 pi, let's say around 2 gigahertz, all this. Okay, let's say for simplicity, just say omega is 2000 giga. For simplicity, assume omega is approximately 2 gigahertz. Sorry, 2 gigaradians per second. Okay, and then let's find what is ZB. Is 1 over j omega. Okay, just look at the magnitude. Just look at the magnitude of ZB. One over omega 2000, 2 gig. 2 gig is how much? 2 times 10 to the power of 9 multiplied by 10 to the power of 15 minus 15. So that's going to give you for simplicity again, I'm going to make this much bigger, 10 gig. Slightly bigger frequency is much better to prove this point. So this is going to be 1 over 10 to the power of 10 multiplied by 10 to the power of 15. So that's going to be 1 over 10 to the power of minus 5. Okay. So that's going to be how much? 10 to the power of 5. So that's going to be 10 kilo ohms. Sorry, 10, no, more than that, 100 kilo ohms. So ZB is very big. It's big, because usually RF signals are very small in millimeter, millivolts, in dBm, millivolts, a fraction of millivolts. So let's say you have 1 millivolts divided by 100 kilo ohms is how much? These are just crude examples. 10 to the minus of minus 3 divided by 100 times 10 to the power of 5. So that's going to give you 10 to the power of minus 3 times 10 to the power 3. So 10 to the power of 5 is equals to 10 to the power of minus 8. So look at the current, the current is going to be extremely small. How many microamps is this? Probably this is like 0.1 nanoamp. Am I right?
Yes, sir. Correct.
So you see the current is so small. That means a very little current is actually going to go through this, right or not? It's negligible. It's literally an open circuit. It's literally, It's literally
Yes, sir.
open circuit. Yes. So that's the thing that we ignore it. Sometimes if it depends on at what frequency you're working on, but in the past I have seen in the simulation that I was doing, I didn't use it at all. Even adding it, I didn't change value very much because the capacitance is very small. A good question. Any other question?
No, sir. So thank you for explaining, sir.
Welcome, sir. Okay, if this is the case, then this model here is sufficient for my analysis, right? This model here is sufficient for my analysis, correct?
Yes, sir.
I'm just ignoring this. So I'm just redrawing that circuit here. I'm just redrawing this. Okay. So what is the input impedance looking into this? Input impedance looking into this is R parallel with, we call this impedance of this is ZC, impedance of this is Z sub L, R parallel with ZC plus ZL. So that's the impedance looking into it. So on this part here, so let's go ahead and like these two things are in parallel. Parallel is 1 R multiplied by 1 over J omega C plus R plus 1 over J omega C. Okay. And then plus ZL. ZL is J omega L. Any question? If I multiply top and bottom by J omega C on this, you're going to get R over 1 plus j omega RC. R over j omega RC. Let me rewrite that. Okay, I would like to do this slightly differently. So I'm going to multiply top and bottom by multiply by j omega c over r. Then I'm also going to multiply this by j omega c over r. So you're going to get, on the numerator, you're going to get 1. Am I right? So we multiply this through 1 by 1. You're going to get j omega c over plus 1r plus j omega l. Are you guys still online?
Yes, sir.
Yes, sir.
Are you all following?
Yes.
Yes, sir. Yes, sir.
So students, now you see right now at high frequency, remember at low frequency, Z was simply R, isn't it? And it's 500, correct? At low frequency
Yes, sir.
in this region. But when you take into the consideration of the parasitics, so like these are the parasitics you have. The parasitics are this, the lead inductance, all this will get magnified at high frequencies. So now when after simplifying, you know that the inductance is frequency dependent. So as frequency increase, it's going to get big. Similarly, here it's 1 over j omega c. So as frequency gets big, that is going to short the resistor out. So using them, considering them, and deriving the impedance gives you this. With this, what can I do? So I'm going to try to plot this Z. I'm going to try to plot the magnitude of Z plot. Plot magnitude of Z. And see how it behaves at different frequencies, at a different range of frequencies. Okay, so are we ready to plot?
Yes, sir.
It's 1 over so I'm deliberately, I would like to keep the equation this way. So in that way, you can see what's happening. Okay, at low frequency, we are starting, okay, we're going to start from low frequency. at low frequency. So you're going to start at low frequency and then you move on to higher frequencies and then see what's going to happen to this magnitude. So I'm only going to do this for once, to show you all these things. With ADS, you'll take care of all these things. But as an engineer, you should know some things. At least must know the fundamental. Why they have this model. Later on, when you go and do in ADS, you'll just simply pull out a resistor, capacitor, and so forth from the manufacturer who already have this model ready. But let's say if you don't have this model, then you should be able to model one by yourself. That's why this exercise is. Okay, let's assume the resistor value, just now I said 200, right? Let's say the resistor, because earlier on I said 200, I'm going to change 500. So I'm going to change it to 200. I'm going to change it to 200. Nothing wrong with 500 because my subsequent example was based on 200. That's why. Sorry about that. So let's say you're starting at 200 right here. This is your magnitude. So when this is omega, when omega is 0, so omega is increasing. So omega not really 0, low frequency, I would say. I would say lower region of frequency where resistors, lower region of frequency when the frequencies is not high enough to cause transmission line effects. Say low frequency. No, you can say approximately low, maybe 10, something like that. Then you go higher region of frequency, 10 to the power of 4, 10 to the power of 5, 10 to the power of say maybe 6, and so forth. So a low range of frequency, you can assume that a lower range of frequency, assume omega is 0. When you assume omega is 0, and then what will happen to Z? You just assume, because at lower range of frequency, definitely omega is not 0. But for analysis purpose, we just assume small frequency means 0. Okay, when you put 0 in this equation, what will happen is 1 over 0 plus 1 over R plus 0, right? In this case, Z is R, which is 200 at a lower range of frequency. So it's still 200 at lower range of frequency. Okay, any question on that?
No, sure. No, sir.
Okay, as you increase the frequency, then it will come to a stage when the parasitics will start to get, where the parasitics will be affecting the impedance. See, somewhere around 10 to the power of 8. Somewhere around 10 to the power of 8. Okay, the 1 over j omega c is doing something. We go back to this equation. Okay, I call this, maybe I call this 1, 1. This is the region 1. So region 2, one over j omega, 1 over j omega c plus 1 over r plus j omega L. Okay, the frequency is now increasing. Frequency increasing, keeps on increasing. When frequency keeps on increasing, what will happen to j omega c? What will happen to j omega c? The frequency increase, j omega c, j omega c. J omega c will be going up, it will also, is also increasing. But the resistor is not affected. Therefore, j omega c, the resistor is constant. So it's going to be getting very, very much bigger than 1 over R, right or not? So the impedance due to the capacitance, the impedance due to the capacitance, this is the impedance due to the capacitance, is going to dominate. Okay, so j omega L also the impedance of the capacitance, called this ZC, let me write this again. ZC is j omega c, will go up, So to the point that ZC will become very much larger than 1 over R. So this is ZC. This is ZL. ZL is also going up, right or not? ZL also, ZL is j omega L. J omega L is also going up. Okay, so the net result is your Z so on this part here, this is going to be just 1 over j omega c, right or not? I can just put ZC because the ZC is dominating. We cannot see, I just put j omega c. J omega c is much, much bigger than 1 over RC. Therefore, you can say that j omega c plus 1 over RC is approximately j omega c. Okay. And then plus j omega L. So this is what's happening. So 1 over an increasing impedance going to bring this impedance down, but plus this impedance is going up, right now. So they're going to be fighting each other. Eventually the capacitance will pull it down. It will eventually pull this down. Okay, then we'll come to a point that 1 over j omega c will be equal to 1 over j omega L. They will come to a point they become equal. That means ZC is ZL. When that happens, there's no more, there will come to a point which implies Z is purely resistive. They will come to a point that it cannot go down anymore, but the inductance will become more dominant. It will start going up like this. So this is called the resonance. This is called the resonance. Resonance where ZC, which implies Z is purely resistive. Okay, let me highlight it again. At this point, it was purely resistive. At this point, it was when it was going down, it was capacitive. So now it's going up, and this is going to be inductive. After that, it will keep on going. That depends on the value of the inductance and the capacitance. We'll come to a point that the inductance become much bigger than 1 over j omega c. So at this point, and then at the point number 3, what will happen is this 3 and this is 2. At 3, as omega increases further, ZL becomes much greater than ZC. Because even though the frequency is increasing, and as you can see that the inductance will pick up after the resonance point. The inductive impedance becomes much larger than the capacitive impedance after the resonance. So after the resonance, Z 1 over j omega c plus 1 over r plus j omega L is controlled by is approximately j omega L. Okay, I'm not going to be asking you to do all these things, but just to show you what can happen at high frequencies. At low frequency, and this is a simple equation, Z equals to R. So simple. And then you go in use this low frequency concept without knowing your high frequency model of the resistor. You think that at high frequency, it's still going to be a straight line. And then you go and design, then your design is going to be a failure. So this is to show you how the resistor parasitics can affect the impedance response. Any question on this?
No, sir.
No, sir.
Okay, I'm not j omega c, right? So if you look at the impedance response, a capacitor, as the capacitance increases, right? As the frequency increases, impedance will go down. Impedance will go down as at omega is equal to 0. Maybe somewhere here, it's coming down. It will completely just going down like this. It is supposed to be a straight line. It should be going like that. But at high frequency, things change. At high frequency, again, you have some kind of right now, I'm just, for simplicity, I'm just showing you only simple parasitics here. The simplified model for a capacitor, you have some, for a capacitor, you have some lead inductance and the resistance. Okay, so it's going to be something like this. The frequency, the impedance response. Okay, so still for inductor, so these are for high frequencies. At high frequency, for inductance, for inductor, it's going to be something like that, okay? It's going to be like this. So they have their own resonance. So as an engineer, you must know that this component have resonance. Are you going to be designing on this resonance? You'll be thinking that, oh, it's just a straight line. And then you go and design, then suddenly you're stuck in this resonance. I don't know, sometimes you may want to make use of the resonance. Sometimes you might want to avoid the resonance. Okay, you have a circuit board here. Okay, just a side view, a PCB. This is a PCB. You guys have seen a PCB, right? Side view.
Yes, sir.
Side view, I mean, I'm not drawing a 3D.
So you mean we have seen the layers, is it?
Just the PCB, PCB, you have components, you have transmission lines, you have chips, and then you have traces moving all over the place, right? You have all kinds of, okay, this is a PCB, okay, PCB, all right? At low frequency, what is the wavelength? At 50 hertz, so you must understand, first of all, you guys have to understand the difference between wavelength and period. A wavelength and the period, same thing?
No.
No, sir.
That's a very strong answer, very good. Okay, let's say this is the wave, sine wave, some sinusoidal wave. Usually the period, I write, you go from here. Let's say this axis is the amplitude, say voltage, Vt, and this is time axis. And this is the period. Period, usually we go from, usually we measure the period from zero crossing to zero crossing. So zero crossing here. Zero crossing, not the zero crossing, the second zero crossing. That's a period. That's one way to do the period. Another way is to peak, also give you the same period. So what is the period for a 50 hertz signal? Period. Calculate, please, all of you.
Zero 0.02, sir.
0.02.
Yes, sir.
Sounds like that. Okay. Period is
1 over
1
F.
over the
1 over F.
1 over the frequency. So 50 hertz means 1 over 50. 50 hertz. So that's going to be
0.02.
0.02 seconds, right? Okay, so that's period. So now I'm asking you, what is wavelength? Two different things, right? You said for the same wave that I have drawn above, wavelength also you can go from peak to peak, same as before, or you can go from zero crossing to zero crossing, and also can have voltage here, but the vertical axis is not time. The vertical axis it's not time. It is wavelength. It can be as a function of wavelength, or it can be in meters. The length in meters. This is time in seconds, right? This is length. Length in meters. So, okay, how many meters? Please calculate the wavelength. We call the wavelength lambda. Is equals to what? Free space wavelength. Kayang,
Yes, sir.
what's the wavelength?
Sir,
Niris?
so lambda equals to C over F, right, sir?
Okay,
So,
what is, okay, so lambda is C over F. Okay, that you got that right.
so I think it's 6 times 10 to the power 6 meters, sir.
That sounds more right. Speed of light is 3 times 10 to the
Times
power of 8 meters per second, right?
Yeah.
And then the frequency is 50 hertz. 50 hertz. So that's going to work out to be
5
600 kilometers. So 600, you said 600, isn't that what you said?
6 times 10 to the power 6 meters, sir.
Okay, 6 times 10 to the power of 6 times 10 to the power of 6 meters. So that is going to be how many kilometers?
600, I think so, sir. 600.
Okay, thank you. So you guys, while I'm at it, I just would like to tell you, for an antenna, for example, consider this dipole antenna. For maximum dipole antenna, you know, right? The dipole antenna radiating waves. For maximum radiation efficiency, the length of the dipole antenna should be lambda over 2. The length should be half the wavelength, lambda over 2. Okay. Let's say if you are transmitting signal at 50 hertz, that means the length of this antenna for maximum efficiency should be 300 kilometers. So you see the point now. Why people use extremely high frequency that has a short wavelength. If you have a short wavelength, you can produce a compact antenna. You know, who can produce a 600 kilometers antenna and fix that to your cell phone?
Yes, sir, I get it now.
I recommend that try to learn something before going out from here. You'll be rewarded. So 600 kilometers wavelength. 600 kilometers wavelength, for example, if I draw this wavelength, let's say this is a circuit. If I take the ruler and measure this circuit from here to here, how many meters is this? Like how many cm maybe? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, around 10 to 11 cm, okay? But this wavelength, man, this is extremely long. If you compare this wavelength, it's a long, extremely long. It's so long, it will look like a DC, right or not? This is the wavelength, extremely long, 600 kilometers. Extremely long wavelength. So the wavelength is very much bigger. So the wavelength, let me call this F, lambda 50 hertz. So the lambda 50 hertz, it's very much longer than the circuit length. Call this length, circuit length. So in this case, there's no transmission line effects. There's no transmission line effects. So that's a point I'm trying to make.
Okay, sir.
So, but when your length of the circuit, if the wavelength is approximately the length of the circuit, then all kinds of transmission line effects will come in. Have to consider transmission line effect. Okay, like we have shown this earlier, right or not? Like you see here, microwave engineering, when the length of the circuit is comparable to the wavelength, okay, that's when we have to carefully design the transmission line. So when the wavelength is extremely long, right? When the wavelength is extremely long, then from here on this side, you are sending a signal at 50 hertz. Then you assume there's no transmission line effect. Then you assume it's instantly available on this side, right? instantly available on the other side. No problem. Okay, this is the length of the line. Okay. At 50 hertz, the lambda is very, very much bigger than the length. Okay, the same transmission line. Now, if the lambda is very much smaller than or comparable, approximately smaller than approximately the length of the circuit, then okay, then you see the wavelength is much shorter. It takes some time to travel, right? There's a travel delay.
Yes. Yes, sir.
There's a phase delay. Somebody's going to smoke, is it? Okay. So there's a phase delay. That's why there's a phase delay. So I'm just giving you some rough idea. You know, we are not going to deep into electromagnetics. We're going to just highlight some things that can help you to graduate, and also at the same time, it will be helpful when you go for interview. Then there's another thing called skin effect. Do you guys still remember skin effect? I remember mentioning this during the signals class. The skin effect, when you have a conductor at low frequency, current is flowing through this conductor. Current is flow of charges, right? So usually the charges are very well distributed all across the cross section. It will cover the entire area, utilizing all the cross-sectional area very well. Okay, at high frequency, when we say high frequency, what I'm saying is that means the wavelength is approximately to the length of the circuit. So at high frequency, what happens? So this can be low frequency or DC. At high frequency, if you send the current will usually travel on the surface. It will travel on the surface. It is restricted to the surface. Leaving empty inside here, there's nothing here. So therefore, the same amount of current flowing through a smaller area. So therefore, it is going to increase the impedance. It's going to increase the resistance. Charges at surface. Charges flow on the surface. So that will bring up the resistance, the skin resistance. It will increase the skin resistance. And this is called the skin effect. Therefore, it is going to increase the losses. So I'm just highlighting, I'm not going to be doing any deep analysis on this. Just highlighting and doing some review. That's all. Later on, we will look at actual electronic circuits and see how to design stuff. Okay, now before we have only a few more minutes, I want to show you the series LC resonance circuit. Have I shown this earlier? A few other Okay, there's also other problems like dispersion, signal loss. As we go along, we will talk about it. So now I want to talk about series. Since I already talked about, okay, now mind, we talk about that the next time. So now, so we have about 20 minutes. So series LC circuit, resonant circuit. So when you have a series resonance circuit, for example, an inductor in series with a capacitor, so L, C, J omega L, 1 over J omega C. If you're looking inside this, okay, at resonance, it's the resonance, this circuit will look like this, short circuit. So this can act as a switch. At particular frequency, it is going to form a resonance that will short circuit. It can short something to ground or can short something to another circuit. So there's a useful application as a design engineer. You might be able to come up with some idea to do things. So why this is shorting the circuits, you can find out by deriving this. The input impedance is J omega L plus 1 over J omega C. And then if you pull out the imaginary part, the J, it's going to be J omega L minus 1 over omega C. If you set this equal to 0, that means you're setting the input impedance equal to 0. And if you solve for omega, that's going to give you, I don't know if you guys you have solved this before in electrical circuits. Omega squared is equals to 1 over LC. So that's going to give you omega is 1 over square root of LC. So you can choose an L and C value to make this, to create a resonance at particular frequency. So you can design that frequency by choosing a certain inductor value and a capacitor. Is there any question? One more quick one, last one. Next, we also have a parallel. The tank circuit is based on this concept. If we look at that earlier, later. Parallel LC resonance circuit. So now you have so about ZP is 1 over J omega C parallel with the J omega L. You guys know how to do all these things, isn't it? 1 over J omega C, J omega L, 1 over J omega C plus J omega L. Then you'll find out that at resonance, At resonance, this will be open circuit. That's another useful application at resonance. So if you want to know how to do that, you can just derive this. If you multiply top and bottom by j omega c, you will get j omega L plus, I don't know how you're going to do it, but try to do it. So you will, somehow you can derive an equation for LC, an equation, omega. So let's do it together and see what happens. Multiply top and bottom by j omega c, when you get j squared omega squared LC. Right, it's raining here. J omega L, j omega c, j squared omega squared LC. So ZP is j omega L. J squared is minus 1 minus omega squared, 1 minus omega squared. You guys know j squared is minus 1. Omega squared LC. So you will try to find what your omega value that will make this open circuit. Can you do that? Because I don't know how to do it. At what frequency? So derive an equation for omega. Derive an equation for omega. How do you, if omega squared, I don't know if I'm doing this right, but you guys please tell me. If omega squared LC if 1 minus, what can make this equation go to infinity? For open circuit, you must have infinity, right?
Yes, sir.
Therefore, what should I do to this equation to make that go infinity?
Must make the denominator, the down part, to become
Equals
near
to?
to, I think near to
Huh?
0 loss.
Okay, very good. Who's that?
Arvindan, sir.
Aravindan. Good. So omega squared is equals to 1 over LC. Then omega is the square root of 1 over LC. So therefore, if you choose the correct value for L and C, any value, I mean, let's say if you want this frequency to be 1 megahertz, let's say 100 megahertz, then you can go and choose your L and C. Depends on the availability at the lab. So you can design your own resonance circuit to open circuit or short circuit.
Okay, sir.
Okay, thank you very much, students.
Thank you, sir.
So this,
Thank you, sir.
okay, since this is the first day, tomorrow please all come on time. Tomorrow we have class, right?
Day after tomorrow, sir.
Yes, sir.
Yeah, tomorrow.